We will pick up from where we left off last class. Again, today we're going to be concentrating on these equations, the Navier Stokes equations, but we've done the hard work already of going through how one can derive the Navier Stokes equations from basic principles, the conservation of momentum and mass. Let me just remind you what we did. Just a couple of snapshots from the previous lecture, just to remind you, or in case you weren't here. This was the basic sort of free body diagram that we drew last class, where we just looked at the x direction of all the stresses. And we did basically a Taylor series expansion around the center of a little cube that is supposed to be infinitesimal and had a volume of dx, dy, dz. And by looking at all the components of stresses in that direction and just doing Newton's law, force equals mass times acceleration, we were able to derive the equations of motion. We got up to that point. The full equations of motions are there shown in blue, just by doing, like I say, force equals mass times acceleration for a very small element of fluid. And I finished by saying that if you specify these equations for the case of inviscid flow, then you would have that all shear stresses are zero. So with the green here, we scratched out all the shear stresses, and the normal stresses would be due to pressure only. And for that case, we wrote the equation in this form, which is the Euler equation. Euler equation is the specific case of the equations of motion in differential form for an inviscid fluid. Also, we assumed constant density. And this is where we left off. This special case of inviscid flow, where we have no shearing stresses. And let me see what I have next. Oh, but they look a little bit different. We still have to develop the Navier Stokes equations. Here I find another picture of Obama with a priceless expression of amazement, or he looks resigned. He looks resigned to the reality of these very difficult equations being something we have to juggle with for the understanding of fluid dynamics, I think. So you see they're a little bit different. Let me go back. The ones in red is the vector form of the Euler equations. That is the specific case of inviscid flow. Now here we have the vector form of the equations for the viscous flow. They're turned around. So what we have in the left here, you see, is the acceleration. In this case, in the right, the acceleration, right? With what we call the local acceleration, or the unsteady term, and what we called, if you remember, the convective acceleration. We wrote the acceleration in this way simply by doing chain rule. I hope you can recall that. So on this equation, we have that on the left. We've just turned it around and divided over by rho the whole equation. So here's the gradient of pressure, which in the Euler equation is right there. And the gravity term is written a little bit different, but it's basically the same. And in addition, we have this term here, which is the viscous term. So we want to explain now how we get to this form, okay? From basically what we have. The full equations here are the blue ones, right? But you notice that we have, in this equation, we have all of the, what are the unknowns in this equation? All of the velocity components, u, v, and w are the unknowns, plus all of the stresses. So there's just too many unknowns. We can't really, that's not really an equation that, even if we add the continuity equation, there's more unknowns than equations, right? The vector momentum equation contributes 3 scalar equations, plus the continuity equation, that's 4. And we just have too many unknowns. So what we need here to be able to get to this form is some relationships between the stresses and velocities. So in the original equation, let me just repeat this. We have the unknowns are U, V, and W, the three components of velocity, plus all the stresses. So basically it's too many because we have one vector equation, the equation of motion, which is equal, of course, to three scalar equations plus continuity, the differential form of the conservation of mass. So this is equal to 4 equations, only 4 equations. Which means basically that we need more information. You agree? Does that make sense to everyone? Yes, right? Now, if you remember, when we started discussing viscosity, that for a Newtonian, we looked at the case of basically just two parallel plates, so it was one-dimensional flow with the velocity in only one direction, and for the case of Newtonian fluid, well, we derived the equation for two parallel plates was we got to tau equals mu du dy. Remember that? That was the simplest possible case of viscous flow. It was all two-dimensional on the plane, infinite parallel plates, and the velocity only went in one direction. There was only a gradient in the y direction. The velocity was only in the x direction. So it was the u component of velocity. But what really Newtonian fluid means is that there is a linear, in general, a linear relationship between the stresses and the velocity gradients. So that's what Newtonian behavior means. Linear relationship between stress and basically this is the shearing strain, or the strain rate, the du dy. We call it the strain rate. So now we'll generalize this to the 3D case. I'm not going to prove it, but I'm just hoping that this makes sense to you from the 1D case that we've already discussed. So if we generalize this idea to 3D, what we have is this. The shear stress xy is actually symmetric, so it's equal to the shear stress yx, and it's equal to mu, the viscosity, times partial derivative of u with respect to y, plus the partial derivative of v with respect to x. So we have basically two contributions of the strain in the 3D case, and we maintain the linear relationship between the strain rate and the shear through the coefficient of viscosity. Similarly, tau yz is equal to tau zy and equal to mu times the partial derivative of v with respect to z plus the partial derivative of w with respect to y. And finally we have the tau zx, which is equal to tau xz and equal to mu times dw, the third component of velocity, dx plus du dz. For Newtonian fluid, the normal stresses Sigma xx is actually going to have a contribution from the pressure and also a contribution from the viscosity in the direction of compression, basically, du dx. Similar for the other components. Sigma yy, the normal stress in the y direction, has a pressure component and also a viscosity component, dv dy. And finally, sigma zz. Yes.
So is that a differential or a 2 for the mu?
It's a 2 mu.
Okay.
2 mu in all cases. 2 mu and du dx. So the component in the the component of compression in the x direction. Basically, if you imagine the viscosity of the fluid resists all motion. So if I compress the fluid, there's also a resistance due to the viscosity there. Now that we have all the relationships between stresses and velocities for the particular case of the Newtonian fluid, we can put this back into the equations of motion, do some manipulation, which will include using the continuity equation. It's about 1 page of manipulations on the equation that I feel you wouldn't gain too much from me just doing it in front of you. But you can see, basically, we're just going to put this guy, all of these, back into the equations. There's going to be a partial derivative of each one, which is going to bring second-order derivatives of the velocity, right? Then you manipulate things, move things around, exchange the, when you have mixed derivatives, you can swap them around so that you can cancel, rearrange things. Use the continuity equation where you have any moment that you have, for example, du dx plus du dy plus du dz. Then you can use the continuity equation because that's equal to 0, and that cancels out, and things simplify beautifully, and you get the full Navier Stokes equations, which I will write without further ado. We will just write them out. Now, for the case of Newtonian fluids, right? Navier Stokes equations, and they will look similar to the case before. I will write them in the same order as we had them from a previous class, where we had the forces in the left and the acceleration in the right, so that it makes sense with our previous notes. We had the gravity component. We have the dpdx, the pressure, and we get these components here that are the second derivatives of velocity. For the first equation, we're going to have always u, the first component of velocity, and we have the 3 second-order derivatives with respect to the 3 coordinate variables. This is also one of the differential operators that we have a name for. It's called the Laplacian. I will write it out in a moment. And on the right-hand side, we still have the acceleration terms. We haven't done anything to those, the same way we had them before. Du dt, and we have the convective acceleration terms, u du dx plus v du dy plus w du dz. So always we're taking derivatives with respect to u in the first equation, and in the second equation we're going to have the same, but with respect to taking derivatives of v, the second component of velocity. So we keep this general. We don't know in which direction gravity points. It depends on our choice of coordinate system. For the time being, we just leave this here. We know that probably we're going to cancel out some of these gravity terms for a particular problem, but we just leave them here for the time being. And now we have the pdy plus mu, the same differential operator but applied to v. So second order differential operator. And the acceleration terms on the right, v now, u dv dx plus v dv dy plus w dv dz. So these terms have not changed from our first, the snapshot that I showed you in the beginning of the class. So now everything is going to be now we're looking at the third component of velocity. So mu, always here's viscosity, and here's w with the same differential operator. All we've changed, of course, is these terms over here by introducing the stress-strain relationships for a Newtonian fluid. I hope you understand my handwriting there. It's not too bad. So these are the Navier Stokes equations, and we can also write them now in vector form. In vector form, we can write rho g, the vector of gravity, minus the gradient of pressure. You see we have dp dx, dp dy, dp dz. And this is the differential operator we call the Laplacian, and we write nabla squared for the Laplacian, and I'm going to use v with a little arrow on top to indicate vector velocity equals rho, and we have the partial derivative of the velocity with respect to time plus just the same as in the Euler equation. This is basically the same acceleration term that appears in the Euler equation. What's changed is the forces. We have pressure and viscous forces. This is the Navier Stokes equations for a Newtonian fluid with constant density. So note, of course, that we've used, oops, my handwriting's lousy there. The definition of the Laplacian, which is second partial with respect to x plus second partial with respect to y plus second order partial derivative with respect to z. And if you need to at this point, you should brush up on your differential operators at home if necessary, just to make it easier on yourself. So now what do we have? So now we have basically our unknowns are still the three components of velocity and pressure. Density, if it wasn't unknown, we may have an equation of state that related to the pressure. So rho is known either because it's a constant density that we can look up in a table and it's a parameter of the situation, or we have an equation of state that relates pressure and density. So we don't need to worry about that one. So we have four unknowns, and we have four equations, of course. These is three equations, but plus continuity. If you recall, continuity was simply that the divergence of velocity equals 0. This is our fourth equation. And here we are. with the Navier Stokes equations. The assumptions of this are that we have incompressible flow and Newtonian fluid. So these Navier Stokes equations do not apply to strange fluids like we saw in the beginning of the course, where you had shear thinning or shear thickening situations. Then you have to do some sort of other manipulations to the stress terms, and you might get a similar equation, but it's not going to be the Navier Stokes equations as we've written them down here. And so the basic quantities that appear in the Navier Stokes equations are weight, pressures, all the viscous forces, and the acceleration, local and convective acceleration. Remember we called these nonlinear terms here. You can see clearly here that these are nonlinear, right? U, du, dx. All of these terms are the nonlinear terms. These are what makes the equation very difficult. The convective acceleration. They appear also in the Euler equation. So Euler equation is basically just as difficult as Navier Stokes because we've got the nonlinearity. That introduces a lot of fun things. Now these equations, the Navier Stokes equations, have no general solution. There are only a few, like you can count them in one hand, or a handful of analytical solutions that one can derive for very special geometries or simplifying situations. But there's no general solution of the Navier Stokes equation. The only general approach is computational. That's why computational fluid dynamics is quite a booming and important field, because the only way to calculate the fluid situations in detail for aeronautics applications, any industrial detailed design of devices that have to interact with fluids, pumps, turbines, and so on, all the wind generation devices, all of the microchips that need to be cooled by air passing through around complex geometries, all of those things, the only way to actually be able to know in detail the flow is through computational fluid dynamics. So we will discuss some computational fluid dynamics, at least the basics of it, later on. Here they are now in the vector form, but I've turned them around. These are the equations that we just derived. I've turned them around. The only thing I've done actually is divide by rho, okay? And I've divided by rho to show the equations in this form, because you'll see these are exactly the same equations that, go back to this guy, the same equations that we have there, right? Just divided by rho. So here we are. Now, so let's discuss some cases, special cases. The first special case we're going to discuss is steady, viscous laminar flow in a horizontal pipe. So because it is steady, then the local acceleration is 0. This term dv dt, right, is 0. I steady. Now, the flow is horizontal, completely horizontal, okay? And so the convective acceleration is 0. Because all of the velocity profiles you do not change along the pipe. We're just looking at flow inside the pipe, and we're steady. The velocity profiles are exactly the same. So if there's a particle in this place and it moves to this place, its velocity is the same. The velocity patterns are going to be the same. Okay, so velocity profiles do not change along the pipe. It is only 1D, only flow in one direction. So basically only one equation is needed. Only one equation for conservation of momentum. And let's for the moment just neglect hydrostatic effects. For just the simplest approach, one can bring them back in, but for the moment let's neglect the hydrostatic, the weight. So what are we left with? We're left with the pressure terms. So remember the full equation, and we don't have the hydrostatic terms, so rho g we don't write. We do have the pressure terms, and we do have our viscous terms. But we only have one component of velocity, so only u needs to be written, the scalar component in that direction. And on the right-hand side, we have the acceleration terms. But local acceleration is 0, convective acceleration is 0, so everything is 0 on the right-hand side. So that is our simplified equation, just like that. So, no, this u is just the component. It's just, remember, we only need one equation because it's 1D. So the v equal to 0 and w equal to 0. So this is just the one. What is your question? What is your confusion? Laplacian?
Oh yeah.
The Laplacian. So basically, we have just this. The Laplacian is, don't worry about it. We're here to learn. Is the second derivative of u with respect to x plus second derivative of u with respect to y, plus the second derivative of u with respect to z. So indeed, the Laplacian can be applied to a scalar or a vector. It's just the second derivatives, the sum of all the second derivatives of whatever it is that we're applying it to. And here we have the gradient of pressure, correctly written out, this would be a vector, and this is not entirely the best way to write this equation, but this is just basically dp dx, okay? Basically, this is only dp dx. Okay, I've just tried to make things simple. So you can see here that this whole equation, really what it represents is this flow involves a balance of just the pressure basically the pressure difference along the pipe, dp dx, and viscous forces. Now this equation can be integrated now. We can separate variables, integrate, and so on, and do things, and I'm just going to write the result here. You can get the expression for velocity in closed form, and it's going to be minus, well, basically dp dx is just p is only a function of x, and so we can write it as dp dx in that form. And for a pipe of radius r, it depends on r squared over 4 mu, and 1 minus r. The little r is the coordinate in the radial direction, and the big R is the radius of the pipe. This is squared. So what we have basically is a parabolic profile. All the velocity is just in the x direction, and the velocity distribution profile it varies in the y direction, right? So different layers of fluid have different velocity. It goes from a maximum value at the center of the pipe to 0 at the walls because of the no-slip boundary condition, which needs to be applied, by the way, to be able to obtain the solution. We need to apply a boundary condition. Yes?
What's the small r?
The little r is just the coordinate in the r direction,
Oh.
and this is the x direction. From the center, yes. This is a particular case where, because there's no convective acceleration, all the velocity, you can see here in this animation that as the particle moves along, very, on a layer inside the pipe, its velocity never changes along the pipe. It's the same value. And so there's no convective acceleration. Remember that what the meaning of convective acceleration was the change in velocity in a fluid particle as it moves from one area of the flow to another area of the flow, where the field values of velocity are different. In this case, the field values of velocity for a particle don't change as it moves along on a straight line. And so no convective acceleration. The velocity profiles are the same in all stations. If I make a cut through the pipe, in all stations we have the same parabolic velocity profile. That's one simple case. Let's look at another one. The other case is flow past an impulsively started flat plate. So what we have here is a plate, flat plate, which is infinite, and everything is at velocity 0, and at an instant we suddenly move that plate to a velocity greater than 0. So again, we're going to neglect the hydrostatic effects. Neglect hydrostatic effects. Pressure is uniform throughout. That's good. But obviously, when I look at this picture, obviously, it's not steady, right? This is the situation. The flow that starts from 0, okay? There's a flat plate that starts from 0. And obviously, if everything is 0 at the beginning and the plate starts moving, because of the no-slip boundary condition, the first layer of fluid is going to be 0, but the rest of the fluid slowly is going to be accelerated by the effect of the viscosity. That is, the plane, the flat plate starts dragging on that fluid, right? And that slowly diffuses out from the plate. Does that make sense? Yeah. Well, it would either be the plate moving or the velocity moving on top of the plate. Either way that you want to see it, there is an effect of the viscosity, right? That there's a no-slip boundary condition right at the surface of that plate. And so if the plate is moving with velocity v, that first layer of fluid is moving with velocity v. It's stuck to it, right? Fluid sticks to the wall. But the velocity varies from v at the surface of the plate to 0, and as time progresses, that kind of diffuses away from the plate. Make sense? And in fact, it is like a diffusion equation. So pressure constant throughout, because this is open to the atmosphere, and so the gradient of pressure is 0. And we have, yes, we do have the viscous term. Velocity is only in the u direction, but the flow is not steady. The convection acceleration is 0. So we have du dt. Convective acceleration is 0 because the velocity does not change in the direction of the flow in the same as we had the previous case, right? The velocity of in the direction of the flow does not change. Convective acceleration. Now this equation then represents a balance between, of course, not unsteady terms and viscosity. The plate, just the only thing it does, it's accelerate the layers of flow above it. That's what it does. This equation, and I think I've forgotten to write my rho, right, somewhere. We have a rho here. The other way to write this is also as we divide by rho and we get nu Laplacian of u equals du dt, where nu is mu divided by rho. If you recall, we saw this a long time ago, so you might have forgotten. We defined this as a property of the fluid at the very beginning of this course, where we were looking at the different properties of fluids. Simply the mu divided by rho is just defined in this way. And so the equation looks a little bit simpler. So when we do that, and it is true that this is kind of like a diffusive effect, because basically this is like a diffusion equation, if you remember for your PDEs. Have you taken PDEs? Anyone? Have you had the partial differential equations course? None of you have. You have, just you. But most of you have not. Yes, yes. Do you have or is differential equations included in any of the other courses that you take, like engineering mathematics or something? Have you seen the heat equation? Does it the equation of heat diffusion? Does it sound familiar? No? Heat transfer. You will only talk about this equation basically for heat transfer. All the course in just one equation. How nice is that? Okay, so you haven't taken PDEs. That's perhaps unfortunate sort of chain of dependency in your courses. It is not a requirement for this course, but obviously we deal with this is, Navier Stoke's equations is kind of the most hard type of partial differential equation because it's unsteady, nonlinear, and vectorial. We have a vector equation, right? So it's pretty hard. Here we're looking at simplified cases. So this one, I'm not going to go over it, but it can be solved. The solution here is, say, we called it the impulsive start of v0. That's the velocity of the plate here, v0. In this case, it's moving that way, v0. 1 minus an error function is, this is one of the functions. You can find it in your function handbooks, handbook of mathematical functions, whatever, or math. You know Math World? Do you know this website, Math World? That one. Error function, you can look it up if you want. And this is the error function of the argument y. Y is in this direction. Y over square root of 4 nu t. And this will pop up again when you study your heat transfer courses. And it's kind of like a diffusion problem. This is a balance between the local acceleration and viscous forces, as I said. So we have here in this animation the development of the velocity profile basically as the effect of the plate diffuses from the upwards, right? In this case, consecutive layers of fluid. Let's look at the next one, which is boundary layer flow. In this case, this is the one that is actually steady, okay? This is the one that is actually steady, boundary layer flow. The previous one was not steady because it was impulsively started, and so the flow, there's some time dependence as the flow gets used to the change that happened there with the plate suddenly started. This case is steady. Okay, and it's called boundary layer flow. Oh, later is a typo. It should say layer. Boundary layer flow. So again, we're going to neglect hydrostatic effects. Then again, the pressure is uniform throughout. This is open to the atmosphere, and there's no reason to. We can actually prove this, okay? That they, sorry, not neglect. We can, and we'll go back to particularly this one. Boundary layer flow is important. We'll go back to it, but for the time being, let's just be content with some physical insight and some physical sort of, considerations. Pressure is constant throughout. So the gradient of pressure term that we had is 0, and now the flow is steady. This is the only difference with the previous case. So you can see where this is going. We have the viscous term, like in the previous case. The velocity is only in the x direction. We have only one component of velocity, but the flow is steady. So all the partials with respect to time are 0, but we do have the convective terms. What we have here, to be clear, is just one little plate. The flow comes here unperturbed and becomes in contact with the flow, with this plate going around this plate, okay? And basically, as it flows along the plate, progressively gets slowed down more and more as it moves in that direction, okay? Because of the effects of viscosity. So in the direction of flow, the velocity is changing because of the effect of viscosity, but it is steady. So if I look at this picture at one point in time, or I look at it later in time, the streamlines and so on will look the same. The velocities will look the same. So this case is a balance of viscous force, viscous effects near the plate and convective acceleration effects. I don't know if this one has, yeah, it is a movie here. Ooh, go back. Don't I have a movie here? Yeah, there it is. Shows you, basically, you see that the profiles are different along the plate. So here, the effect of the plate is felt basically very near the plate only. As the fluid progresses further down, the effect of the plate is felt further away. You see that this profile has a different shape than this one in the cartoon here. This one already starts getting complicated enough that we are not going to be able to write a closed form solution. Velocity depends on both x and y. It's already getting difficult. Why? Because we have this nonlinear term here. So already this is an equation that we have trouble with, okay? There are approximations and so on, and some ways of analyzing this, but already we can't write down a closed form solution. We can see that the effect of the flat plate is being felt on a wider and wider region as you go along. Basically, the idea is that the boundary layer thickens in the direction of flow. That's the concept of boundary layer. We will come back to boundary layer later on. The next example of flow here is inviscid flow past an airfoil. In this example, we have it's steady, it's inviscid, and therefore there are no viscous forces, viscid equals no viscous forces. So basically, we're neglecting again the hydrostatic effects for simplicity. They're small. And so we have pressure. And on the right-hand side, we have the... I don't remember in the previous equation for the boundary layer flow whether I wrote mu or nu for the viscosity. It was nu. Okay, correct then, because I didn't write rho on the right-hand side. So just to be clear, in this case I'm writing my rho here. I don't have viscosity. The viscous terms are 0, but I do have. I'm going to. In fact, I'm just looking. So we're doing like an approximation that the velocity. This is suppose an approximation that the velocity in the y direction is almost 0. So you can sort of just look at the v component, but not entirely right. If we wanted to be really correct, we would write the full equation, and v would be a function of both x and y. But we don't have a closed form solution. In this case, what we have is, what we can see from the equation is that it is a balance between pressure gradients and convective acceleration. Sorry, I got carried away. I forgot that we usually take a break. And we probably should right now. That's all I have to say about this guy. There's nothing more to say. I mean, we can't find a closed form solution. And all we can say is that it's a balance between pressure gradients and convective acceleration. So already to do something like this, we'd have to do a computational approach. Let's take a 10-minute break.